Okay, so I'm going over 1.5, which is complex numbers. This is something that I'm pretty sure nobody's ever really seen before. It's not really anything that you ever see until you start getting to college, basically. So this is probably brand new for most people. And I'm actually going to go into a little bit of the history of them to kind of dispel the myths. So, looking at basically a little history of the imaginary unit. So, this came about because people were trying to find solutions to equations that involve negatives inside a square root. And they're like, what do we do with this? Because we have this equation, it seems like we should be able to find this solution. So, um, the work on complex numbers and imaginary numbers started in the 1500s, but they didn't really get officially named. They were described, but they were not named until 1637. Rene Descartes named them imaginary because he thought they did not exist. And this is why I think it's a bad name, because they do exist. They come up in nature. They're used a lot in electricity. So these are things that exist. So they're not imaginary. They're not really made up. So it's a terrible name. But back when people were talking about these, they didn't know that they existed, which is why they called them imaginary. Isaac Newton used these when he was trying to find solutions to cubic polynomials. So we've talked about polynomials, and 1.4 talks about quadratics. A cubic has an exponent of 3. So he needed imaginary numbers in order to solve those kind of things. Then Leonard Euler, and he'll pop up again in week 7, he was the one that actually decided that he was going to call it I, and he defined I as being the square root of -1. And then he's the one that also gave us a way to visualize these things by coming up with this graph. So you can graph complex numbers if you have the real numbers as your horizontal and then imaginary numbers as your vertical. And so that gives you a way to start visualizing these things. And all of that was happening in like the 1600s. Then we get to 1831 and Carl Friedrich Gauss. He didn't like the term imaginary, which I agree with him, because by that time, by the 1800s, it was pretty much accepted that these things really exist, especially because that's about the time when people start working with electricity and they realize how useful these things are. So he decided to call them complex numbers. And so that is like the preferred term, but I is still called the imaginary unit, and we still use imaginary numbers. So we use both terms. Complex number is specifically when we have both an imaginary part and a real part. So this is the definition of a complex number from the textbook. What I want you to focus on is that it's written a plus bi, where there's like a regular number, a real number, plus an imaginary number. So you have both parts. So technically all of our numbers are complex numbers, but the imaginary part is 0. So if it's written a plus bi, like 2 plus 5i, that's called standard form. And that's the I part is called the imaginary number. And if it doesn't have a real part, if the real part is 0, then it's just an imaginary number. So there's this graph. That way, the real numbers, that's everything we've worked at so far. And now we're adding in imaginary numbers, and you put those together to get complex numbers. So like a real number could be 2, an imaginary number could be -3i, and then the complex number would be 2 minus 3i. So you have like 2 parts to it. So when we work with complex numbers, you can pretend that the I is like a variable, and then it follows the rules of algebra. So when you add them, that means you add like terms. You add the real parts together, you add the imaginary parts together. When you subtract, you again treat them like terms. When you multiply like normal. You can FOIL, you can use the rules of exponents. The only exception is I squared. Because when we multiply, we usually end up with an I squared, and I squared is defined as -1. So after you do your multiplication, you replace I squared with -1 and simplify further. So we should always end up with just something with a real part and an imaginary part, and we won't have any exponents. And so that we're allowed to say that I squared is -1 because if I is the square root of -1, then when you square both sides, that undoes the square root and you end up with -1. So that's the only different thing when it comes to working with complex numbers. And then when it comes to dividing, that's a different process as well, because you have to multiply the top and the bottom by what is called the complex conjugate. And so the complex conjugate has the same real value, but is the opposite for the imaginary value. Okay, so if we have that complex number 2 minus 3i, its conjugate would be 2 plus 3i. So you just change the sign in front of the imaginary part. So these are complex conjugates. And we multiply by the conjugate because that allows us to eliminate the imaginary part for the denominator, because we don't like to have an imaginary number in the denominator of things. So I'm going to go through basically lots and lots of examples of all sorts of things you can do with complex numbers so that you have a good base. First, find real numbers a and b such that a plus 2 plus b minus 2i equals 4 plus 7i. So basically, this a plus 2, that's our real part. So a plus 2 has to equal 4, which means that a has to be 2. Then the imaginary part, because on the right we have 7i, that means b minus 2 has to be 7. So we can add 2 to both sides, and that gives us b is equal to 9. So you can, when you have an equation here, and you can directly compare the real part to the imaginary part, and they need to be equal if you have an equation. So like the rules of an equation still hold when you're working with complex numbers. Now, second example here, this is where you have to start taking things into complex numbers, and this is useful for the quadratic formula for when you start solving, because that's where you get square roots with a negative inside. So I've got 2 minus the square root of -18. So we have a negative in the square root, and previously to now, you would just kind of say, oh, there's no solution, there's nothing you can do. But now we know there's something we can do, because now we know that there is I. So I need to rewrite this. So I'm going to take, if we have the square root of -18, this is the same thing as the square root of -1 times the square root of 18. So I'm just separating out that negative from the actual number portion there. And our definition of an imaginary number is that I is equal to the square root of -1. So that means I can rewrite this as 2 minus I, and then I have the square root of 18. Now we need to simplify the square root of 18 because we always try to simplify radicals. So 18 is 9 times 2, so I can split that up as the square root of 9 times the square root of 2. I just move over to the right. Now the square root of 9 is 3, so I can simplify this. And we usually put that number in front of the I. And then I like to put my square root in the back so that the I doesn't look like it's in the square root. So I would write this as 2 minus 3i times the square root of 2. Alternately, you can write this as 2 minus 3 times the square root of 2 and then have an I. But it gets confusing because you have to make it very obvious that the I is not inside the square root. But you can write these either way. They're equivalent, basically. The book will always write it the second way, But I just think that's prone to too much confusion. So I always put my I before the square root so that we don't have any confusion there. My basic rule is whenever I have a negative in the square root, I describe it as pulling out the I, because if I pull out an I, then it becomes positive in the square root. So that's usually what I will say, and I won't write the step above it. I'll just write an I in front and then remove the negative sign there from the square root, because that's basically what you're doing. Okay, so now I have an example of adding and then an example of subtracting here. And so you're basically doing like terms. So these complex numbers are in parentheses just to indicate that we're adding two complex numbers. But because there's no negative signs in front of the parentheses and there's no numbers in front of the parentheses, the parentheses are unnecessary. So we can just write it without them. So we have 13 minus 2i plus negative 5 plus 6i. And then we want to combine our like terms. So the real numbers, 13 and negative 5, those are like terms. So you would do 13 plus negative 5, which is 8. And then you add the imaginary parts. So those are considered like terms. It's if you have a variable there. So a negative 2i plus 6i. So negative 2 plus 6 is 4. So that gives us plus 4i. And then that's your answer. So if you pretend your I is like a variable like x, the same rules apply when we are simplifying with like terms. Now with subtraction, we have to distribute through the parentheses just like we would with any other expression where we had like variables. So my 3 plus 2i, I don't need those parentheses in front. And then I'm going to distribute the negative to get a negative 6 and a negative 13i. So now we combine our like terms again. So the 3 and the negative 6 are like terms. 3 minus 6 is negative 3. And then the I portions, the imaginary portions, are like terms. So that's 2i minus 13i, which is negative 11i. And then that's your answer. Okay, now when you get into multiplying, there are little extra steps that do make it a little bit more complicated. And so I'm going to just write here that. So I is equal to the square root of negative 1, which means that I squared is equal to negative 1. So we really need to use that I squared equal to negative 1 bit. So my first example, I have two complex numbers multiplied together. We can FOIL, just like as if it was x instead of I. So you still go through the FOIL process. So that's 7 times 3, which is 21. And I have 7 times negative 5i. So you multiply the numbers, which would give us negative 35i. So it's just like it's x. Then I have a negative 2i times 3. So that would give me a negative 6i. And then negative 2i times negative 5i. So negative 2 times negative 5 is a positive 10. Then I times I is I squared. So far, so good. Now we want to replace the I squared with negative 1. So we have 21 minus 35i minus 6i. I'll make my eyes not get messy. Plus 10, and then I squared is negative 1. So now that's 10 times negative 1. So now we need to start simplifying. So I have 21. I can combine my i's. Those are like terms. So negative 35i minus 6i is negative 41i. And then 10 times negative 1, that's minus 20. And then I can do the 20 minus 21, which is 1. So we get 1 minus 41i. So the difference here when you're multiplying is that you have to take that I squared and replace it with negative 1 and then continue simplifying. Because I squared in this case is not really a variable, it's actually a value. We're just treating it like a variable to do the multiplication, and then we have to replace it with what it's equal to after that in order to simplify. Okay. Now, the second one here, this one we have 5 minus 4i squared. So when you have something squared, you could use your shortcuts to multiply, or you could write it twice. I like to write it twice just to make sure that I don't mess it up, and then go through the FOIL process. So we've got 5 times 5, which is 25. Then 5 times negative 4, so that's minus 20i, because I have that I there. Then negative 4 times 5, that is another negative 20i. And then negative 4i times negative 4i, so that gives me a 16i squared. So I can already, I'm going to do multiple steps at once. I'm going to combine my negative 20i's because I can add those like terms. So that gives me negative 40i. And then that's 16 times negative 1. So we have to replace that I squared with negative 1 again. So then we get 25 minus 40i minus 16. So, okay, 16 times negative 1, that is negative 16. I've done that part correct. Now we need to do 25 minus 16. So 25 minus 16 is 9. So we get 9 minus 40i. Okay, so when we have fractions here and we're trying to simplify them because we don't want to have imaginary numbers in the denominator, we need to multiply by the complex conjugate, which is the opposite sign of the imaginary part, and you pick the one that's in the denominator. So I need to multiply by 1 plus I. So I'm just switching the sign of what is in the denominator. And I need to multiply that on the top and the bottom. And that means on the bottom I have to actually FOIL. So you have to then also do multiplication. So I'm going to be hoping that I left myself enough work or enough room here. So I'm going to put everything on the left. So on the top, I need to distribute the 13 through my parentheses. So that gives me 13 plus 13i. Now in the denominator, I need to FOIL. So I have 1 times 1, which is 1. Then 1 times I, so that is just I. Then I have negative I. And then a negative I times a positive I is a negative I squared. So I FOILed in the denominator, and then I distributed in the numerator. And now I want to simplify. So the top, I can't really simplify further. And the denominator, the I minus I, those cancel. That's why we multiply by the conjugate, because we want the i's to disappear. And then I have 1 minus, and then I squared is negative 1. So you want to be very careful about your signs here, because a lot of people will miss that it's minus negative 1. So you want to be very careful with your signs. So I have 13 plus 13i, and then 1 minus a negative 1 is 1 plus 1, so that's 2. And then we usually split this up so that it would be 13 halves plus 13 halves I, so that it is in standard form, so that we have the real portion separate from the imaginary portion. So now the second one here, we have 2 complex numbers, one in the top and one on the bottom. You want to multiply by the one that's in the denominator in the bottom. So we need to switch the sign in front of the imaginary part. So that'd be 1 plus 2i. And so I need to do that on the top and the bottom. And so now I'm going to be FOILing on the top and FOILing in the denominator. So let's see, 6 times 1 is 6. 6 times 2i will give me 12i. Negative 7i times 1 is negative 7i. Negative 7i times 2i is negative 14i squared. In the denominator, 1 times 1 is 1. 1 times 2i is 2i. Negative 2i times 1 is negative 2i. And then negative 2i times 2i is negative 4i squared. So now I'm going to combine my like terms and convert the I squareds to negative 1. So I have 6, and then 12 minus 7 is 5, so that's plus 5i. Then minus 14 times negative 1. In the denominator, I have 1. 2i minus 2i cancels. Then minus 4 times negative 1. So now I need to just continue line. So I have 6 plus 5i plus 14. And then in the denominator, 1 plus 4. So I'm going to just kind of move down to the left on the bottom. 6 plus 14 is 20, so that's 20 plus 5i. And then we have 5 in the denominator. And so then we split it up. 20 over 5 plus 5i over 5, which reduces to 4 plus I. Okay, so now I'm moving into, a little more complicated. You're not going to see something like this very often in real life, but I wanted to do this example because this would give you more practice with rational expression where you have to get a common denominator. And that's essentially what you need to do here. You need to get a common denominator. So I'm going to multiply 1 by 2 plus I, and then the other one by 2 minus I. And if you notice, these are actually conjugates, so that's going to cancel our denominators out very nicely. And then we'll have no imaginary numbers in the denominator. That doesn't always happen. Sometimes once you multiply by the and get a common denominator and then you add them, you then need to multiply by the conjugate. So it's like you have to combine multiple steps. But I started this one out with, these are going to cancel out nicely for us. So the first fraction, I need to distribute the 2i through. So that gives me 4i minus 2i squared. And then when I FOIL in the denominator, I get 4, see, plus 2i minus 2i minus I squared. And then second fraction I need to distribute. So that gives me 10 plus 5i. And then I'm also going to get the same denominator. So now I'm going to start simplifying. So the first fraction, I'm going to replace the I squared with negative 1 while I can. And I'm going to do that in the denominator as well. The 2i minus 2i cancels. So that's 4 minus, and then I squared is negative 1. Then second fraction, 10 plus 5i, and I get 4 minus negative 1. So now I have 4i plus 2, and then 4 minus negative 1 is 5, plus 10 plus 5i over 5. So now when I add these, I add the like terms. So I add the real parts, 2 plus 10, which is 12. And the 4i plus 5i, 9i. And then the denominator is 5. And then we split this up. So that's 12 over 5 plus 9 over 5i. Okay. So now I'm going to go back to the square roots because these are the things that you're going to see when you're doing the quadratic formula. You're going to see things with square roots with negatives in there, and there is a specific order that you have to do things when you have things with imaginary numbers. The imaginary number has to be basically taken out of the square root first before you do anything else, because otherwise you can get two possible answers. And so as mathematicians, we had to make a decision on which is the correct answer if you get a different answer with different ways. And so you always take out the I first. So this top example is a perfect demonstration of that. So if we have a square root of -5 times square root of -10, this is not square root of 50. You do not just multiply the -5 times -10 and get a positive 50. That would not give you the correct answer. The correct procedure is to remove the negative inside the square root by writing it as an I, and then you multiply. So I would have an I times, I'm actually going to move this to the left. So I have an I times the square root of 5, and then I remove the I from the square root of -10, so that's I times the square root of 10. So I have to remove the negative sign inside the square root by making it an I first. Then I multiply. So I times I is I squared, and square root of 5 times square root of 10 is square root of 50. So now we need to start simplifying. So you can see already there's a difference because I squared is -1. So I get a -1 in front, and then that would be -1 times square root of 50 instead of square root of 50. So there is a difference in these two answers. So the order matters here. And then 50 is square root of 25 times 2. So I can take the square root of 25, and that's 5, and I can multiply that by the -1. So I get a -5 in front times the square root of 2 instead of 5 times the square root of 2. So the order matters, and the rule is take the imaginary portion out first. And that means everybody will make sure they get the same answer. So everybody will get the -5 times the square root of 2. Now, this second one is another demonstration where this could go wrong, because when we don't have imaginary numbers, we are told that you can sort of flip-flop the square and the square root and put the square inside and then put the square root on the outside. If you did that, you would square first, get a positive number, take a square root, you'd get a positive result. You would get a positive square root of 76. But when you involve negatives inside the square root and we have imaginary numbers, we have to do this in a certain order so that we don't get contradictions like this. So you have to remove your I first. So I pull out the I, and then I have the square root of 76, and then squared. And so you square the I, which is I squared, and then you would square the 76, or the square root of 76, and those would cancel. Actually, let me really write that out. So I squared is -1. The square root and the square cancel. So the real answer here is -76, not, oops, should be positive 76. So when you have imaginary numbers and you start having that negative, you start getting into these parts where you could potentially get contradicting answers. And so the rule is always take that I out first so that everybody gets the same answer. Now this last example, again, we're going to take the I out first and then we're going to start simplifying. So square root of -45, that is I times the square root of +45 minus, and then that square root of negative 5. I'm going to take out the I, and that gives me the square root of 5. So now the square root of 45, I can simplify that because that is the square root of 9 times the square root of 5. And the square root of 9 is 3. So this is 3i times the square root of 5 minus I times the square root of 5. These are considered like terms because they both have the imaginary unit and they both have square roots of 5. So I can do this as 3i minus I, which is 2i. So this will give me 2i and then times the square root of 5. Or you can write this as 2 square root of 5i. So you pull your I out and then you simplify your square roots just like you would anything else. And then in order for things to be like terms, they both have to match with the square root and match with the I.